Hey everyone, and welcome. In this video, we dive into convolutional neural networks, or simply CNNs. Right now you see two small filters sliding across an image and producing two brand new feature maps. Those little rectangular boxes of weights move over the picture, sample local neighborhoods, and provide a summary value which they store in the feature maps on the right. That is the visual heart of a CNN. Notice how the filters analyze only a few neighboring pixels at a time. Because of that, the network can recognize a shape no matter where it appears. This built-in shift resistance is called translation invariance, and it is the first big idea we tackle today. Zoom in on a single pixel. This diagram breaks the local calculation apart. On the left, the dark blue square is the filter of size 3 by 3, the numbers give the input pixels, and on the right, the blue upper left cell receives the final response of this filter position. Then the filter moves along all input data positions and fills the right output field, the feature map. The math looks a lot like a fully connected layer, but limited to a tiny patch. Spelled out, xi equals the sum over every xj in the neighborhood, any. Each xj is multiplied by its matching weight wj, and then we add a single bias b. Using local patches rather than the whole image slashes the number of learnable weights and makes training far easier. Here is an example. The input data are given on the left. The filter weights have been trained before. They are multiplied at each position and then summed up, which yields 26. After that linear combo, we squeeze the result through a nonlinear activation function called sigma. So yi equals sigma of xi, where sigma could be a rectified linear unit or any other favored activation. Our little 3 by 3 filter has been at every position. The feature map has been pre-filled at the top. Then we add a bias b that we assume to be -1 here, so we obtain the lower preliminary feature map. Finally, we apply the real U activation function, which retains only positive values. The lower right is our feature map of this filter. Why is this weight efficiency possible? Because the very same weights get reused at every location, an idea known as weight sharing. Each reused filter produces its own feature map, the two layers you see on the right. Multiple filters mean multiple feature maps and richer learned representations. Stack a collection of these filtering operations plus activations, and you get a full convolutional layer. 2 filters, 3 filters, or even 20, each layer can learn an entire bank of visual patterns. Let's count how many parameters appear in a practical example. Here, yijf is the output at position ij for filter f. We loop over k and l, which span from -1 to +1, covering a 3 by 3 window. And over c equal 1 through 3 for the red, green, and blue color channels. Every term x sub I plus k, j plus lc is multiplied by its weight w sub klcf. Then we add 1 bias bf and wrap everything with sigma. That entire filter needs only 27 weights plus 1 bias, so 28 parameters per filter. 2 filters mean just 56 learnable numbers. Compare that with more than 6,000 in a tiny fully connected layer on the same image. Efficiency is the game changer. In general, the total parameter count equals the number of input channels, NC times filter width, and W times filter height, NH times the number of filters NF plus 1 bias per filter. Crucially, image resolution never shows up in this formula, so adding megapixels does not explode the weight count. Next, let us talk about a few housekeeping tricks. First, padding. Those extra 0 rings let a filter sit on the image edge, so we keep the spatial size intact. Second, striding. By jumping 2 or more pixels at a time, we cut down the resolution on purpose. Third, dilation inserts holes inside the filter, which widens the effective view without extra parameters. Finally, pooling, whether we take the maximum or the average, shrinks the feature map and keeps only the most important signal. Changing topic, this graphic shows the receptive field of view growing with depth. Early filters see small local patches. Deeper filters integrate over larger and larger chunks of the original input. Here you see the classic convolutional pyramid. As spatial dimensions shrink, the number of feature maps expands. That pyramid is the essence of hierarchical learning, initially simple edges, later full objects. After several such spatial stages, we usually flatten the tensor into a long 1D vector and hand it off to fully connected layers. That transition lets the model build high-level associations among the extracted features. Be careful though, large flattened tensors can spawn millions of weights. Tricks like global pooling keep the parameter count under control. To wrap up, here is a direct comparison of a 1D convolutional layer at the top with a fully connected layer at the bottom. In the convolutional weight matrix, the horizontal filter holds 3 weights, which are shifted to the right during the convolutional operation. The weight parameters are shared. The fully connected matrix, by contrast, requires a unique weight for every entry. But only the diagonal band holds weights, and the same 3 weights repeat on every row. Thus, the symmetry-based reduction slashes computation and memory without sacrificing modeling power. So there you have it, convolutional neural networks, translation invariance, weight sharing, feature maps, and all the supporting operations that make CNNs the workhorses of modern image and signal analysis. Thanks for watching, and keep exploring.